last session, two presenters, airplane performance analysis through CFD results, assessment of NACA 648212, wing body combination by J.I. Abeygoonewardene and RMPS Bandara. Both of them are senior lecturers from KDU. One, the rank is not there, but I know she is an Air Force officer. Senior lecturer of Aeronautical Engineering of General Sir John Kattawar of University KDU. Her research interests include flight dynamics and cooperative and autonomous behavior of unmanned aerial vehicles popular in Pakistan. She has served the Sri Lankan Air Force as an aeronautical engineer for the past 16 years. Her teaching area include aerodynamics, aircraft stability and control, and air breathing propulsion. And RMPS Bandara is a senior lecturer of mechanical engineering. Sir General Kotla KDU, Sri Lanka. Actually, he is the head of mechanical engineering also. And Sri Lanka research interest includes computational modeling, optimization of energy systems. At present, he holds the position of head of Department of Mechanical Engineering. Has 16 years of both academic and industrial experience. His teaching area include thermodynamics, heat and mass transfer, and product of Morato University also. It's not here. Yeah, Mr. Bandara.
Good afternoon, ladies and gentlemen. The topic of our presentation is airplane performance analysis through CFD results, assessment of a NACA 64A212 wing body combination. This is actually a joint project done by Squadron Leader Jeevani Abeygoonewardene and myself. I am Bandara. And we have organized our presentation according to these topics: overview, research objectives, the governing principles, methodology and approach adopted during this study, results and interpretation, and limitations, and finally the conclusion. Let me elaborate on the overview. The performance of an aircraft can be analyzed in terms of both fluid and flight dynamics. And fluid and flight dynamics can be assessed based on different perspectives, and three such perspectives will be for better aircraft handling, for better engineering design, and for better results in training if the aircraft is a trainer aircraft. But unfortunately, most manufacturers do not reveal such technical information to the users. Maybe due to they consider it as a trade secret, so that they are at a disadvantage if they reveal it. So because of this reason, the users will not be able to optimize these machines, especially when it comes to training. If the trainer knows how to optimize the trainer aircraft or the machine, will be able to use it very productively, so that both the instructor or the trainer and the student will benefit from it. So on this basis, we thought of bridging the information gap between the designer, manufacturer, and the user and handler by analyzing an existing wing body combination and trying to generate our own set of data, set of technical specifications, so that we could make use of the technical information in optimizing the performance of such systems. This has some link to the previous work that we have carried out and that we have presented during the last KDU symposium in 2013. Actually, we analyzed a 2D NACA 64A212 airfoil. That's a 2D case using CFD. Why we use CFD? Because in engineering you have three modes of analysis, that is analytical, numerical, and experimental. Experimental is of course too costly. Analytical can be applied when the problem is very simple. So we actually used numerical analysis, and for that we used computational fluid dynamics. And through that research, we actually generated the generic lift curve and drag polar for the 2D airfoil, and two-dimensional flow for subsonic and transonic regimes were observed during that research. And this will give you some of the results that we presented during the last symposium. You can see some of the curves, performance curves in terms of lift, drag that we generated, and also the drag polar, and also some of the contours of velocity and static pressure. So based on this, we have put one step forward, and we have gone forward to model a 3D case where we have NACA 648212 wing body combination. Through same approach, CFD approach. So this is a 3D case, and the route is modeled by a NACA 64A114 airfoil to represent an actual wing. So the research objectives is, as I said before, to model the aerodynamic behavior of the wing body combination using the CFD methodology, and to correlate the results to the aerodynamic performance parameters related to flows of reasonable Reynolds numbers that are encountered generally during actual flight. So that is our research objectives. And if you look at the governing principles, mainly we are using Navier-Stokes equations, which are very complex because we are handling real flows. So there are three types of Navier-Stokes equations: all partial differential equations, continuity, that will give you the conservation of mass, and conservation of momentum in terms of x momentum, y momentum, and z momentum. I'm not going to explain them now. They are all partial differential equations. And energy, which will set up the enthalpy and energy levels. And also we have looked at the resultant aerodynamic forces that are acting on the aircraft. As you know, closer to the aircraft, the viscous effects are dominant, and when you go far away, the pressure forces are dominant. So we have to look at them separately. This is the methodology that we have adopted. Actually, we are using several tools in this case: a solid modeling tool, a main CFD tool, and visualization tools. And Gambit 2.3 is our solid modeling tool, which is we can actually create our solid model, or you can import it from another solid package like AutoCAD. We can incorporate boundary conditions and physical geometry, and once that is done, we can export it as a mesh file, and the computational model is set up. And then we can export it as a mesh file and can import it to the main CFD tool, that is Fluent. And Fluent, we can incorporate other boundary conditions, flow properties, and the turbulence model. The greatest challenge was to select a turbulence model, because there are so many turbulence models, and we have gone for Sparat-Almaraz because according to literature it is the best model for this type of external aerodynamic flows. And then you run the simulation, and if we get a converged numerical solution, then it's okay. But if you have some problems with the simulation, like the simulation might crash, or it might have instabilities, then you have to go back to the computational model and see where you have gone wrong. So it's an iterative process. And this is the computational mesh that we have created, a 3D mesh, and it consists about 1.3 cell volumes, 3D volumes. The problem was we have to have a compromise between the accuracy and the computational time and resources. So we actually had a compromise. We optimized the number of cells that has been included, and use this computational mesh. And if you look closely, the wing, we have changed the resolution from one place to the other. On the boundary close to the vicinity of the wing, we have a very fine mesh, but towards far or distance places we had a coarse mesh. This is in order to compensate with the computational time.